Okay, we begin this afternoon's session, which is also the closing session of the conference, but before we turn to our speakers, we have a word from Angrid.
So I just want to say something about the posters. So those of you who have contributed with posters, so at the end of the day today, if you want to bring them with you, you should take them down. Because we can connect them, but in the end we don't have as much space at Nordita. And also, if you contribute with posters, please send us a PhD of the poster and then we put it on the webpage.
Okay, so we begin this afternoon with David Dunbar, and he will tell us about the maximal supersymmetric Gluon QCD.
Oh, thank you to the organisers for the invite to speak. What's been, well, at least up to now, a very enjoyable week, very animated. So this is work together with my colleagues Guy and Warren, who are sitting over there. I won't point the laser pointer at to swap them out, so it's worked together with them. And at the moment, we're all still EU citizens. So it's a little summary. What we're going to talk about. There'll be an introduction. This should be an introduction. And then I'll talk a lot about the 5 Gluon 1+2 loop amplitude in QCD. That's not our calculation, but I will talk about it quite extensively. And then I'll talk about some techniques about unitarity and augmented recursion. And then I'll talk about higher point functions in QCD yet to loop again. And then some possible extensions and conclusions. So introduction. Well, obviously for this audience, I think we all agree that amplitudes are important, which is true. Analytic expressions are particularly interesting. That's something that most of us have always been interested in. And the simpler the better. A lot of what we've done has been about simplifying things, better understanding, find structures and move on. Slightly differently, maybe we don't all agree on this one, is to actually look a little bit beyond n=4 super Yang Mills. The results which have been presented at this conference of n=4 super Yang Mills they're just achingly awesome. They're absolutely fantastic, but it is interesting and important that we take these ideas and go beyond n=4 out into other theories. So we've heard a lot that n=4 is the hydrogen atom of the 21st century, so we have a nice picture of glowing hydrogen there, which we love and understand because it's a perfectly solved problem. I was trying to think of the punchline for the next bit, and actually, I'll leave it to you to think about what the analogue of QCD is. So what physics of the 20th century is like QCD now. So I'm leaving that as a puzzle for you to think where QCD is. If n=4 is the hydrogen atom, is QCD, is it deuterium? Is it solid state physics? Is it building houses? What is the analog? What's the extension? How far from n=4 to QCD do we have to travel? Okay, so I'd like to start by a bit of history or prehistory to look at the one loop, all plus Gluon amplitude. So this is the QCD amplitude. The all plus amplitude vanishes identically in supersymmetry. So it's a specific amplitude which doesn't exist in a supersymmetric theory. Now, my title was Maximally Symmetric rather than all plus, and that's slightly deliberate. It's the all plus amplitude. So when we study n=4, our amplitudes are being simplified by what's happening inside the loop. For the all plus amplitude, it's then simplified by what's happening outside the loop. So it's a sort of simple amplitude, but it's simplified by the outside rather than the inside. And the inside, there is still QCD. So that goes way back to the early days of the history of the subject in '93. There's some features of the amplitude. The tree amplitude vanishes, and it's finite and free of polylogarithms, which is very unusual for a one-loop amplitude related to the first comment. It was first obtained by collinear limits, which in today's language is its factorization or its singular structure. So it's been obtained by singularities. It's a lovely looking form, which looks cyclically symmetric until you actually look at it. And it's actually the legs 1 and 4 have been selected specially, so actually the form is not manifestly supersymmetric. But when you actually look at it and do the sums and work it out, it turns out to be. So it's more symmetric than it looks. associated with the discovery or the writing down of this amplitude, from the simple analytic form, there's what you can take forward from that. So this actually coincides with the amplitudes of self-dual Yang-Mill, so people looked at that. And a feature of this, from the very early days of CSW, looking at MHV vertices, it was realised that this is something which intrinsically is difficult to calculate from MHV vertices directly. You cannot do a diagram for this particular amplitude. It's very intrinsically a non-supersymmetric. It's kind of at the core of where you get away from n=4 on. It also has a sort of interesting dimension shifting relationship. Now, putting this up partly because it's an interesting in itself, but also just to point out a few features. This is the all epsilon form of the one loop amplitude, and well, there is an all epsilon form. So though it's a finite amplitude at epsilon to the 0, when you expand out all these integrals, it picks up logarithms and polylogarithms at the orders in epsilon as you develop along there. And bizarrely, there's a very bizarre relationship between QCD amplitude and n=4, which if you write it in the all epsilon form and shift epsilon to epsilon -2, or equivalently d goes to d plus 4, the n=4 amplitude, once you pull out the factor of ij to the 4th, it coincides at all orders in epsilon to the QCD amplitude. So there's a kind of fascinating link between n=4 and QCD tucked in that one there. Okay, so that's a little bit of history. Let's look at the 5 Gluon to the all plus amplitude. To be careful, I'm looking at the leading in colour, I'm looking at the unrenormalised amplitude. And it was written down, not by me, or it's by someone expressed like this. So it's written down as a 2-loop amplitude. It has a factor of the 1 loop outside, it has a singular piece, and it has a remainder piece, and it has order epsilon tucked in like that. Now, this was first computed at the integrand level using d-dimensional unitarity techniques, so cutting and cutting and cutting, integrals putting it all back together again, and you should get your big sort of proper, if you wish, 2-loop integrals to actually perform to calculate this out. And subsequently, it was integrated and presented in this form by German, Hen and Presti. So I actually quite like this as an example of how sometimes with QCD, it's a bit like trying to move this great big heavy object. So someone drags it along a couple of meters, drops it, someone else comes along, picks it up, drags it a couple of meters, drops it, and eventually the ball actually gets to where it's going. So it's kind of been picked up in 2 stages to be written in its present form. Now, the function left over is finite, f2, f5, and you can split it into a polylogarithm piece and a rational piece tucked in like that. The singularities match general theorems by Catani, and I'll point out that the a5 to the 1 is the order epsilon piece. So all the pieces I showed previously, order epsilon, they're up there, but they're sitting out front, multiplying the singularities. And this is it. And I actually got really excited when I saw this, because it's a genuine 2-loop amplitude, QCD, and it fits on a page. Really nice, really simple. So the summation here is over the 5 cyclic permutations of A, B, C, D, E, and you get some dilogarithms tucked inside. So that's the polar logarithmic piece. There's a rational piece, which has this ubiquitous factor, which you see in both the MHV amplitude and the 1-loop QCD amplitude, tucked in like that. And then it's multiplying some very, very simple kinematic variables. S's. There's a trace here. This trace here is tucking away some quite interesting double poles. So there's an angle 4, 5 there. When you expand that out, it starts to square 4, 5. There's 2 of them upstairs, cancels one of the square 4, 5s downstairs, so you end up with a singularity, which is square 4, 5 divided by angle 4, 5. So there's a nice double pole in there. So, I mean, this is it. And I just thought, wow, how can that possibly be hard to calculate that? I mean, let's say, so it looks so nice, it somehow, it should be easier, there should be other ways of getting something so nice, perhaps, is that it? Now, first comment is the particular combination of dilogarithms, top here, they can crop up in various places. They crop up in 1-loop computations, and there are 2 ways of thinking of them. They're either a 4 either a 4-dimensional one-loop integral where you've truncated it by chucking away the epsilon pieces, or it's actually the 8-dimensional one-loop box. So there's a scalar one-loop box there in 8 dimensions, and that gives you exactly that combination of polylogarithms. Okay, so that got us quite excited looking at it. So we thought, well, point out first of all, it's a great result. It's the first 5.2 loop QCD amplitude computed using d-dimensional unitarity plus extensive integration developments. So the idea was to try and reproduce this using some sort of blended approach. The first idea is, well, there are general theorems for the singularities, let's use them. Okay, let's not calculate something which is there by general theorems. Let's actually just somehow put it in almost to start with. And then we decide, well, d-dimensional unitarity is hard. So I'd actually much prefer to use 4-dimensional unitarity. So the idea is, we'll not do it quite right, but we'll use 4-dimensional unitarity, and we'll use that for the finite pieces. The idea is that the epsilon mistakes we're mistaking by using 4-dimensional unitarity, well, they'll get the leading bit wrong, but for the finite piece which doesn't have a 1 over epsilon in it, at least we've got a fighting chance that 4-dimensional unitarity will work for that. And then we're going to use recursion, augmented in some well-defined way to pick up the finite piece. So it's a kind of blended approach, but generally based on the singularity structure of the amplitude in different singular forms to try and calculate it. So first of all, unitarity. So the one loop all plus, it doesn't have 4-dimensional cuts, so just treat it as a vertex. And then it sort of becomes a pseudo one-loop calculation. And you can expand the amplitude in one-loop integral functions. So it's 5 points, so there'll be a 1-mass box, there'll be a 1 and 2 mass triangles, and there'll be a bubble, and that's it. So there are a plethora of techniques for calculating integral functions using unitarity. You do your cuts. A quadruple cut can give you the box, triple cuts will give you the triangles, double cuts will give you the bubbles. So there's I could fill a couple of slides with people who've worked on this and done stuff. Actually, that's the first time I've used the C. I meant to drop the C from my name, because my name's David Cameron Dunbar, so that's just not a good name. So I'm not going to say that. I'm now going to clean the C's out from all my existences. I don't think I can do that easily on Spires, unfortunately. Okay, so there's a lot of techniques. We use particular ones. We use something called canonical forms, but you know, it doesn't matter as long as you get the answer. Okay. Well, I have talked about the 5-point, not the 4-point. The 4-point's a lovely calculation also. Sometimes doing recursion, you need to go far enough to actually recurse. And it's a little bit unfortunate in that if I do this with a 4-point amplitude, there's no box present. So somehow the 4-point is just a little bit too simple actually to sort of bootstrap from. We needed 5. And also, usefully, although you can use 2 particle cuts for this, the answer is 0, which is really nice as well. Okay, so we can compute the coefficients as a pseudo one-loop amplitude of the 1-mass box. And the 1-mass box is this particular combination, as promised. Well, it's got 1 over epsilon pieces, singular pieces at the beginning, and then it's got the finite polylogarithms, which we've been looking at. So the box integral splits into singular terms and polylogarithms. So those are the singular terms, that's fine, and then those are the polylogarithms. So you kind of split them up and send them different ways in the calculation. Now, so the singular pieces we send off to the leading term in the amplitude, which we know by general theorems, and it's the finite pieces we keep. Now we also have 1 and 2 mass triangle functions to calculate, but I won't present the coefficients for them, that's so important. There is a huge consistency check. I said we want to chuck the IR pieces away because of general theorems. As a consistency check, well, we get them in the 1 mass, we get them in the 2 types of triangles. When we add all these coefficients together, it's kind of important that we get at least the leading term of the singular, which we know from general theorems. So that we actually do, as a consistency check, get that. Now what we get is actually missing the 1 over epsilon pieces. We only get it to epsilon to 0, so we have to kind of promote that to the full amplitude, which we knew was there anyway. Now I say it's important that you remember there is stuff here, I'm pointing it out here. This 8-dimensional box is tucked in this one loop amplitude. It actually carries an epsilon in front of it, so these one cancel. So when you do the expansion, like this, up in here, pieces do hit the 1 over epsilon squared piece. So in fact, although the whole, as I'm showing it, it looks like a one-loop amplitude. It's not real. This is not really a one-loop amplitude. There are genuine higher polylogarithms tucked in here, but it's just they're pushed off to the singular piece of the bit and stuff, so we don't really need to calculate them directly. That's quite good. So we've got a piece left. We get the polylogarithms which work out. And so we need to use the rational terms. So we know how to deal with rational terms in amplitude, complexify momentum, and then we do carry out shifts, and we get the BCFW recursion. So that would be fine. I would point out alternative shifts are available. This is what I call the Casper shift after Caspar-Reiser. It's actually the conjugate of this shift. But here we shift the two momentum, we complexify them, keeping momentum conservation. But there is an alternative way of doing it which only shifts the lambdas, and then also using the Schouten identity that also keeps momentum conservation. So I need that one. I need to point that alternative out. So we can form the rational object, which is just the two-loop amplitude, take away the bits which are not rational, and what should be left should just be the rational combination. So although it's a two-loop amplitude, you take away all the stuff you know which it's got all the cuts in it, and you're left with a rational term. So you want to do recursion on this bit that's left over. Now, there are some problems. So we want to apply recursion. Well, unfortunately, although the amplitude has beautiful factorization properties, the pieces themselves don't. So this split, in fact, this piece here, it contains lots of spurious singularities, so which actually means that R5 also has spurious singularities of equal and opposite sign. So the spurious singularities have to cancel across the bit. So these spurious singularities are a pain in the neck, obviously. I say but known. Once you calculate F5cc, then you know them. They're not known from any principles or anything. They're known because first you calculate this, and then you get extra spurious singularities, which R5 must also contain. You know it has to have these because this whole thing has to cancel out. And I say we do need the 4-point at this point to apply recursion to, so we need to get the rational part from the 4-point amplitude out. With this remarkably binary-looking hep number. Someone stayed up very, very late on the Millennium Eve to get that number, I think. So is that 001? What's it? So is that 17 in binary or something? Okay, so anyway, so it's a very binary-looking hep number, but there is a 4-point from 2000, which we can actually get the rational terms from and use them for recursion. And a more physical problem, the spurious singularities, they're spurious, they're not physical. There is a sort of physical issue that when we're using complex momentum, amplitudes can have double poles rather than single poles. And also, as a technical issue, when we do this with the straightforward BCFW shift, we actually find that it doesn't give good behaviour at infinity. So as a technical issue, we have to use the Casper shift, which actually has good behaviour at infinity for the amplitude, which allows us to reconstruct it. Okay, so why double poles? Where are they coming from? So for real momentum, amplitudes are single poles. Double poles arise when we've actually got complex momentum. So if I draw a diagram like this, and you did it carefully and properly, you'd find out that the one loop has an expression like this, and there is a 1 over k squared divergence in that bubble coming out. And that combines with the 1 over k squared divergence from the propagator to give a 1 over k squared squared. So there's a double pole in there. Again, this is something very specific to non-supersymmetric theories. So, so this is something which vanishes in supersymmetric, so you don't worry about this. But they kind of pollute calculations of gauge theory and gravity. There is a pain in the neck when you're calculating recursively gauge theory and gravity calculations. Now, at one loop, they're not, well, they're kind of evil, but they're not omnipresent. The all plus at one loop doesn't have them, because if I try pulling off a 2 pluses here, I have a minus, and a single minus tree vanishes. So actually there's no double poles in the all plus. The single minus does have them. So if I pull off the two pluses here, I've now got 2 here, so this is an MHV tree amplitude, and that wasn't. So the single minus is completely polluted by them. The MHV, if you try with the MHV, you have to pull off a minus, and you need at least 2 pluses, and that means actually n greater than 5 means it only appears for 6 points. So although they appear in MHV amplitudes, they don't appear in the lower point MHV. Slightly surprisingly, for next to MHV, they don't show up until you're at 7 point. So actually they're there in one loops, but they're not there in the 4 and the 5 point amplitudes. They only really crop up when you actually start calculating multi-legs, and they can pollute them quite badly. They're not a problem, really, if we knew everything, because Cauchy's theorem applies whether there's double poles or single poles. So if the amplitude is a double pole and a single pole, that's not a problem. The residue is just that combination there. But what we do need is we need both the coefficient of the leading term, and we also need the coefficient of the subleading term to evaluate the residue. So we really need formulas or calculations to work out the subleading singularities. Now, at this point in time, there are no general theorems there to help us. There are some examples with the form of one loop, but really, it's kind of problematic what the subleading pole is. I got very excited by the work with the soft theorems, because I think the soft theorems are a fantastic example of where there are theorems for subleading behaviour, but there are no subleading theorems for factorisation, unfortunately. Now, essentially, we need off-shell behaviour, because if this side of the diagram is 1 over p squared squared, this current we have over here, well, we have to expand it to p squared a0, which is the p squared equals 0 piece, and then there's a p squared offsquared piece like that. So we need some sort of recursive techniques to get the subleading pole. This is what I think we term augmented recursion. I forgot to put it up there. And we need to work at least partially off shell to get into that subleading pole and calculate it. And I mean, this is something that Warren's actually been much more driving and developing than I have on the techniques of it. Somehow I just don't go, I'm too old to go off shell somehow or other. It's just, off shell doesn't suit me. But Warren's really driven this forward in that. And using light cone gauge methods, which keeps the plus and minus structure that we're so familiar with on-shell amplitudes, turns out really to be the best way to do it. So basically you have to do a kind of integral which looks like an off-shell current, and there's a double pole crops up in here. This itself contains a pole, which is the leading double pole, but it's the sub-leading piece which is critical to get, and you actually have to get the sub-leading piece from both sides of the diagram, so you have to calculate a current like that. So it relies on working off-shell. It goes back to some of the ideas of off-shell currents, which go back a long way. And it can be very cumbersome, but it does produce a result. I mean, some of the examples we've used at one loop have produced correct, but very, very cumbersome formula coming out. And it's mostly we've used it mostly in gravity. So the current we needed here, it's an approximate current. It's not the genuinely off-shell object, that's too hard to calculate, but it contains enough of the leading behaviour near p squared equals to 0 to determine the subleading pole. Now from this I'll just pick out, it's using light cone methods. This is an off-shell current, so alpha and beta are off-shell legs, and it introduces a reference spinner Q into the process, which hopefully drops out at the end of the calculation. Okay, and well, the answer is it does. So to cut to the quick a little bit, using the augmented recursion for the subleading poles, using Cauchy, putting it all back together again, we correctly reproduce the 5-point amplitude using this. The rational term needs cleaning up quite a bit to reproduce the known result, but then I'm told that the output from the integrals also needed quite significant cleaning up before it also was written in the lovely form that it's been written in. Okay. So that's nice. So it's nice to reproduce this and see how some of the features could arise from things other than the direct integration methods. Okay. Now, so can we push it forward for any more legs for the all plus endpoints? So again, we start as before. So I split my amplitude into a singular leading piece, which looks like this. I have a finite piece, and again, I split my finite remainder as before, like that. Now, just to point out where some of the things are hiding in this, if I'm doing 6-pointer, I need a 6.1 loop here, and this is the actual expression for it, so it contains all these lovely integrals with all the hard dilogarithms and trilogarithms which are in the amplitude, but we've peeled them off into here. So we're hopefully that the bit that's left over is amenable to other approaches. Okay, so we calculate the polylogarithmic pieces from the boxes. So there will be two mass boxes in this case. One corner would be one loop, the tree on the other side. And the singular pieces, again, is a major check, and it's quite non-trivial, that the pieces, they all add up to being the one loop times the 1 over epsilon squared piece. Again, this is something we've checked numerically up to 30 points. It's not something which we can even remotely start to calculate analytically. Well, maybe someone stronger than we are could show analytically, but that's numerically checked up to 30 points, because it's very unobvious how it's happening. And we can put the leftover bits are the polylogarithms. So the function in this case is related to the 2-mass truncated Ox function, or alternatively the d equals 8 version, which is non-singular like this. So this is the integral, and the summation is over things which look like this. That gives the labelling, and that's just the coefficient. So the coefficient's kind of quite nice and happy, and there's this ubiquitous form at the front here, sort of nicely like that, existing still to 2 loops. Okay, so that was for endpoint. Now I don't have endpoint results for the rational terms. We've got them for 6 points. So that's where we are at the moment. So the rational terms can be written like this. Again, I have a ubiquitous denominator, and I have some function upstairs like this. Now, what came out of the augmented recursion was a rather large Mathematica file. Okay, so I'm not showing you the large Mathematica file, I'm trying to split it up into some sort of physical structure which can be understood. So I'll split it up into 5 bits. So the first term, set of terms we can understand quite clearly. We can arrange them by the singularities. So these terms have multi-particle poles in them. So there's a 1 over TABC in there. This is different from the 5 to 6 point, so we have multi-particle poles corresponding to singularities in the amplitude like this. This particular pole, as you can see, it factorizes into the 4-point all plus and the 4.1 minus at one loop. So the 1 minus amplitude is coming in to pollute this particular result in some way. So that works quite nicely. Almost an immediate consequence is I've had to introduce spurious singularities into the problem. So I've got these expressions underneath like this. So when k becomes null, this very nicely splits up into a square dk, angle ka, which are exactly the spinors which I need for things on the other side. So I've organised it by the multi-particle poles, but they almost drag me immediately down to reintroducing spurious singularities into my expression. So those have to go away eventually. So that works well. So I've introduced them. Now I need to have double poles in my expression because the amplitude has them. Now in a way, this was sort of guaranteed to work because we built it from the double pole, so it had the correct double pole in one channel. Now, it was in some sense you know when you've got it right, when your amplitude becomes cyclically symmetric, because the recursion breaks the symmetry of the legs, and that only gets restored when you've actually got everything back up. That's one way we know that the standard recursion didn't work, because what we got back didn't have the proper symmetry. So using the other shift, we get something which is properly symmetric. So since we built it from one channel, it's guaranteed to have the other channels working. Okay, so I have the double poles in here. There's a pole out front from the ubiquitous factor, and when these come in here, they give the double poles. Again, I'm still running around with lots of spurious singularities. So I have to add something. So we had to sort of decide what needed to be there to get rid of the spurious singularities, and it sort of looks like this. So these spurious singularities there's some complicated expression in front of them like that. Now, of course, these are the bits I can somehow or other motivate. So we take a large Mathematica file, we subtract the bits we can motivate, and we get left with a bit at the end. So the last piece, it's pretty simple. I have no motivation for that other than it's the bit that's left over. Okay, that's the bit left. That's organised according to some something like that. But of course, you wouldn't get that if you only drove it via the spurious singularities, etc. So we have an amplitude, and the amplitude satisfies some quite nice things. It satisfies symmetries and gauge independence. That's the gauge independence. The augmented recursion uses off-shell behaviour. So off-shell, there is a gauge momentum Q comes in, and it's a major test again that we get things right, that actually the Q dependence drops out of the physical expression. And again, as I say, it has the proper cyclic symmetry when it tucks in like that. So that's quite nice. It has proper singularities. The whole ansatz does because it is. And has the correct collinear limits, which we check in various channels tucked in like that. The collinear limits are quite nice because although I split the amplitude into 3 pieces, the collinear limits they talk to each other. So actually they impose constraints back and forth between the different pieces. So the collinear limits, they kind of tie things up together. So that's quite nice. We had to assume that the one loop goes smoothly to the one loop n-1. Now, for the low points where we could actually really do the integrals, that was possible to check analytically, and it worked in quite a complicated way. And I think it's kind of obvious at higher points, but certainly that's some sort of little nagging, can't quite prove it in some bizarre sense. Okay, for the all epsilon form. Okay, and we have the correct factorization, and rather nicely, the rational terms have been actually confirmed by a sort of, that's a d-unitarity computation. So actually, so from d-dimensional integrands, they've actually been able to check that the rational terms have been confirmed, which I guess if I left the last one, all the other ones probably are kind of irrelevant. That's how it progressed through. So, can it work for anything else? Is this just a single trick that works for a single amplitude? Maybe, I don't know. Now, for n greater than 6, we don't have it. We don't have the rational terms. I think it's doable. Well, it's obvious we can do it, but it's. I think the 6 point has got a lot of structure to it, and I really don't think the 6 point has been written in an optimal way. There's probably lots of different ways of writing it which emphasise different features. So I suspect some of those features would actually, probably worthwhile exploring them before sort of naively just pumping it back up to 7 point. It might be rather difficult to sort of simplify the 7 point, and I'm not sure leaving it as sort of a couple of megabytes of Mathematica file is really very helpful to anyone. So we'll probably do that, but I think we'd really like to. I don't think there's any point in doing it unless we can express it in a simple form. The other example is a single minus. Now, I have twin daughters, and so sometimes you have twins, you have good twin and bad twin. So here we have the good twin and bad twin. So there are 2 finite one-loop amplitudes in QCD, the all plus and the single minus. These both vanish in supersymmetric theories, so they're both intrinsic to non-supersymmetric cases. The all plus is the good twin. The single minus is the bad twin. So it has a much more structure. It's always harder to calculate for most cases. So it's also very interesting to see how bad it will be. Okay, so I think we haven't got that yet, but I think we'd like to try getting the single minus just to somehow compare it, to have some more spectrum of what the good and bad of the QCD amplitudes is tucked in there. So that'll be quite an interesting one to see. It's got lots of different features from the all plus. It has less symmetry, of course. And of course there's gravity as well. So for example, as a pure speculation, well not speculation, if I do the same for gravity, I can also have a proposal for the polylogarithmic part of the gravity amplitude, which has a kind of rather nice sort of form like that. This one has, one thing I say here, rather slightly nicely, the O plus, I talked about things being difficult by spurious singularities. The spurious singularities weren't too bad for the Yang-Mills case. That EC to the 4th is quite a nasty spurious singularity in the gravity case. So that'll have a sort of rational descendant which contributes to the rational terms in there. Right. So, to conclude, well, it is the first 6.2 QCD amplitude. It's not a next to leading order because its interaction interface term would be with the one loop. It's actually an n cubed LO. So it's it will be a very, very small piece of the 6 on next cubed Ergo calculation. So, and the 5 and the 6 point, I think, are remarkably simple. So the 6 is getting more complicated again, but it might be massaged a little bit into better forms. So these are remarkably simple amplitudes. I think that is certainly a major surprise to me when I saw how simple the 5 point could be written down. And most of the worst logarithms of the problem are tied in, and we know about them from the general theorems. And it's just nice to have a little window into the higher loop QCD, just to see a little bit further in there and just get a peek into higher loop QCD. And again, it's also really nice to see simplicity outside n equals 4. So it gives you hope that there actually will be simplicity outside of n equals 4, and there will be interesting structures which can be explored outside n equals 4 like that. And I guess one of the things, well, again, I don't know who I'm talking to, the converted, if you can calculate something using singularities, one should, because it will almost always be better. So singularities are a great way to calculate things. And that's... oh, gosh. Okay, and that's me finished.
We also thank David for finishing in good time, and so we have time for questions.
At one loop, there's a relation between a plus QCD and X4, and actually by dimensional shift, and is there some hint at two-loop level?
I've heard it said, I can't see it myself. That's something very interesting to explore. The 6 point n equals 5 is largely Lance has got his hands on that, and I can't quite see it. It would be certainly interesting to explore that sort of link. It's not as simple as just shifting the dimensions on those integrals. It's certainly not as simple as that. But there's hope, I think, of finding links between them.
Other questions, David? I'll give you mine.
You mentioned the gravity as well. I suppose that's pure gravity.
Yes.
Do you have a proposal for the case where you have axials and dilatals as well?
I guess the answer is simply no.
Okay, but maybe it's easy to get. I mean, it should be very similar, right?
Yeah, we have thought about the QCD about other states of matter in there, and of course, factor advantages in supersymmetry does allow you to talk things out. I don't have an answer to that. In terms of cutting, the one loop is proportional to the number of states.
Yeah.
So the remainder function would match, most of it would be proportional to the number of states.
Yeah. So it's just a one loop. Right?
Yeah. But there might be other bits.
Any other questions or comments? I don't see any, so let's thank David again.